The satellite motion describes a certain limiting case in orbits where we take the mass of the satellite, ms, to be a lot less than the mass of the central gravitating body, right? In this case, the mass of the Earth. Now, in this limit, where ms is much, much smaller than the mass of the Earth, the approximation here, we take this, this kind of limiting case here, what we're essentially doing is saying, we're going to take the Earth and just fix it, nail it down in place. Okay. In fact, what's happening is the Earth and the satellite are both orbiting around their common center of mass. Okay. Their common center of mass. But you can imagine, since satellites have a mass that's incredibly small compared to the mass of the Earth, that you can kind of neglect the fact that the center of mass of the Earth satellite system is offset a tiny, tiny bit from the actual center of mass of the Earth, right? So this approximation then of satellite motion gives you a perfectly circular orbit. And that's really nice. It simplifies things a lot. It's a very good approximation. Although, in fact, all gravitationally bound orbits are in fact ellipses. They're elliptical orbits, not in fact circular, but they're really, really close in the case of, say, a satellite going around the Earth. They're really close as well in the case of planets going around the sun. This is a less applicable approximation, but it's been done and it works for some of the planets quite well. Anyway, so that's what we mean when we say satellite motion. When we say satellite motion, we're making this approximation where the mass of the outlying orbiting body is very, very small, and that gives us then circular orbits, not elliptical orbits. So let's just talk a bit about launching satellites. You need to launch a satellite very, very, very carefully. You need to launch it at a speed that's not too small. If the speed is too small, right, then you're just going to crash into the surface of the Earth, as this trajectory right here traces out, right, smash into the Earth. If you launch it too fast, then the thing could either escape, right, if the velocity at which you launch it is greater than the escape velocity of the Earth. Escape velocity is a concept that we'll cover after we've talked about conservation of energy a few chapters down the road. It could also end up in this very strong elliptical orbit, and then in that case, right, it would head way out here if you launch it too fast, and then it would kind of look almost like a comet's motion, right? It would, in all cases, other than if it crashes into the Earth, end up right back where it started with the exact same velocity at which it was launched, because that is a property of gravitational orbits. In fact, it's a property of any two objects that are held together by some inverse square distance law. So charges, for example, they would always end up, they're perfectly periodic. They end up at their starting point with their starting velocity after some amount of time. But if you hit the exact Goldilocks zone, then you'll end up with a nice, stable, circular orbit going all the way around. Okay. So let's talk a bit more about satellite dynamics. So, as I said, we'd be on a circular orbit. We know that for uniform circular motion, right, the centripetal acceleration is equal to the velocity squared, the speed squared, divided by radius r. For a satellite, right, the gravitational force is the centripetal force that's holding the satellite in its orbit. So the force of gravity then is equal to the mass of the satellites times the acceleration of the satellite, equal to mass of the satellites times its speed squared divided by the radius of the orbit. Now keep in mind here, this radius is the distance from the center of mass of the Earth out to the distance here of the orbit. Now don't let this thing that looks like a cannon here fool you. I did mean for this to be some kind of a launch, right? This is supposed to be an appreciable distance out from the center of mass of the Earth. But this is the relevant distance here, not the height above the Earth. I can plug in then Newton's law of universal gravitation on the left-hand side here, and you'll notice here I can cancel out the mass of the satellite on either side. I can multiply by r on both sides of this equation. Get rid of that, get rid of the square there. And if I take the square root of both sides here, I've just derived the velocity of a satellite. That would be square root of g, Newton's gravitational constant, the mass of the Earth, divided by r, the radius of the orbit. So here is the speed of a satellite, a distance r above the center of mass of the Earth. All right, we just found the equation for the speed of a satellite going around the Earth, a distance r from, a radius r from the center of mass of the Earth. Notice here that the velocity, the speed at which this satellite is going around, does not depend on the mass of the satellite itself. It only depends on the mass of the Earth, of the central body that it's going around. So let's use this equation now in doing an example problem. So this is an example problem from your book. Find the height of a geosynchronous satellite. Okay. Geosynchronous just means that the time that it takes for an orbit is equal to the time that it takes for the Earth to spin around its axis. Okay, that means that the satellite essentially is going around at the same rate at which the Earth is going around. So the satellite sits above the same location then on the Earth, right? So a geosynchronous satellite then could kind of hover above, say, a city, as long as that city's pretty close to the equator. Okay, so a geosynchronous satellite, and it wants us to find the height of the geosynchronous satellite, not, so that would not be r here, right? It would be the height would be the distance above the Earth's surface. So here I've shown r to have two parts. It has the radius of the Earth and this height h here. So we can write, in this case, r is equal to the radius of the Earth plus h, the height from the Earth's surface out to where the orbit is taking place. Okay, so how are we going to go about solving this problem? Well, I like to use SI units, so the period for a geosynchronous satellite is going to be 1 day, or in SI units, 86,400 seconds. And I need to find then the height given the period t, and given that this is a satellite, so we know the velocity in terms of the mass of the Earth and Newton's gravitational constant. We always will take for everything in Chapter 6, we'll always take values like the mass of the Earth, the mass of the Sun, the distance to the Moon, the distance between the Earth and the Sun. Things like that are going to be taken to be known quantities. You can get them from the inside cover of your textbook. I've also posted on Blackboard the inside cover pages of the textbook so that you'll have all of these astronomical numbers that you need to do your homework and things like that. So we're given t, and we're going to solve for h. All right. And this is, because it's a satellite, an object in uniform circular motion. So we have a bunch of tools at our disposal, all of the equations for uniform circular motion and the newly derived satellite equation. So an object in uniform circular motion, right, will have this speed, g, that's the Earth, divided by r, and an object in uniform circular motion has 2 pi, travels a distance 2 pi r within its period t. So I can take this equation and rearrange it to solve for the relationship between r and t. If I square both sides, I'll get g mass of the Earth over r on the left-hand side, and on the right-hand side I'll have a 4 pi squared r squared over t squared. Okay, I'm going to divide 4 by 4 pi squared on both sides and multiply by r on both sides. Divided by 4 pi squared. And multiplying by r. Bring this power here from a 2 to a 3. Okay. Note the radius cubed divided by the period squared is equal to this value here, which is a constant. Now, this we'll come back to in a minute. It's called Kepler's third law. We'll get there in a minute. Kepler's third law actually holds in the case of elliptical orbits as well, not just circular orbits. So that's interesting. The radius, the height h is what we're looking for, and so we can solve for r over here, and then we can get h. So if I multiply by t squared on both sides and then take the cube root, I would have r equal to g and the Earth over 4 pi squared times t squared, and the whole thing to the 1/3 power. Okay, I'm not quite done yet. I have this distance r, which is from the center of mass of the Earth out to the orbit, and that would be equal to then the radius of the Earth plus h. So to get h, I just need to take this quantity and subtract the radius of the Earth off of that. So I have h all in terms of known quantities here. If I plug in these known values for the mass of the Earth, the radius of the Earth, which you can get from the inside cover of your textbook, and plug in for t, 1 day or 86,400 seconds, then I get that the height would be 3.6 times 10 to the 7th meters. And that's about 6 Earth radii. Sorry, I had to shift things around once again. We are limited for board space here in the physics basement. Last thing to say is just that this relationship here is Kepler's third law in the case of a circular orbit. The radius cubed over the period squared is equal to some fixed value that depends only on the central gravitating body. This is a very interesting law, historically speaking, because this is also true for ellipses. Instead of the radius here, you would have the semi-major axis of an ellipse. And as Kepler showed us, the planets travel around the sun in elliptical orbits. So Kepler derived this relationship and completely revolutionized the way that we look at planetary motion.